Hello dear students. So, we are discussing the gradient drift. The objective of gradient drift is to understand the plasma motion in a realistic magnetic field. What is a realistic magnetic field? Realistic magnetic field will never be uniform and will always be curved. It has to be curved to obey the Maxwell equations, right. So, we will continue our discussion of, we have derived an expression for the gradient drift which is V del B, the gradient drift as minus plus V perpendicular RL by 2 BZ dou BZ by dou Y along x cap, right. So, we have understood what is the approximation that we have used for this, for obtaining this expression, right. Now, the lines of force in our last discussion were assumed to be coming out of the plane of the paper, and we have also defined the gradient. Now, let us say if the lines of force are not straight, but they are curved. So, you have a line of force which is curved like this, right. Now, what will happen in that case, right. So, if they are moving from, let us say if they are moving from north to south, what will happen? How will the plasma motion be different in this situation? Now, for this, let us consider the magnetic field B parallel to the phi cap direction. So, you are looking at the cylindrical coordinates now. So, let us say we have x cap and we have y cap, and we have this z out of this plane. Okay. So, this is the radius RC, and we define phi cap in this direction, or the angle itself as phi, and the unit vector which is denoting the increase of the angle away from the x axis is phi cap. So, this is the angle phi, and the unit vector, the corresponding unit vector is in this direction. Okay. Now, the radius of curvature is, let us say if a magnetic field line is like this, we can say that the magnetic field line is now parallel to the phi cap, right. So, the magnetic field line is going like this. Now, since the magnetic field line is not a straight line, rather it is curved, the radius of curvature is denoted by this RC cap. RC cap is a unit vector. The radius of curvature has to be defined with respect to the center of the coordinate system, and you say this is RC, and the increasing direction is, since this is RC, RC cap has to be this. Both of them are same actually, right. Now, the configuration that we have taken is the magnetic field is parallel to the phi cap. What is phi cap? Phi cap denotes the direction in which the angle phi is increasing, and what is angle phi? Angle phi is denoted in a counterclockwise direction away from the x cap. So, this is the frame that you have, this is geometry that you have taken, right. So, the magnetic field line is parallel to the phi cap, and the angle is measured away from the x axis and towards the y axis, right. Now, if you are taking the cylindrical coordinates, we will write, so our equation is still the same. What is it? The force is equals to Q times V bar cross B bar. This is still the force. But we take a cylindrical coordinate system, we write the respective equations as we take R component, Z component and phi component. These are three. So, the R component equation, so you can also write this as rho Z phi like that. The R component So, if you take any basic mathematics textbook and refer to cylindrical coordinates, you can get these equations, the derivative, how they are written in different coordinate systems. So, we will write m times r double dot minus r phi dot square is equals to minus q times v cross b. You will only take the r component, the radial component. The velocity v is defined in Vr, V phi, Vz. The magnetic field B is now 0, B phi 0, right. So, V cross B, V cross B can be evaluated as I j k Vr, V phi, Vz 0, B phi 0. So, if you expand the cross product, we can write the radial component the choice of unit vectors could be r cap, phi cap and z cap. After expanding the curl, we can write m r double dot minus r phi dot square is equals to minus q minus Vz B phi, or it is equals to q Vz B phi. M r double dot is equals to q Vz B phi plus m r phi dot square. So, r double dot is dimensionally equal to ma. This is equals to the acceleration, right. So, what you have is the momentum equation, which is ma, the force, is equals to sum of the component due to the magnetic field and a component due to the magnetic field which is along phi cap, right. So, this is the acceleration term. We understand this much, right. What have we got? We have got a term which is because of the magnetic field and mr phi dot square, and if we write the z components, m d Vz by dt as minus q Vr B phi. So, because of the curvature of the magnetic field, we have got an additional term. So, inhomogeneity in the magnetic field now appears through B phi, right. That is the basic idea. So, B phi, the additional term, is basically due to the curvature. So, you write the additional term, just take out the additional term, F is equals to m RC, because we are looking at RC for a particular flux line which is along RC cap. So, V phi, you should remember V phi is R phi dot. Okay. Now, this is the additional force that the particle is experiencing. Now, we can evaluate the curvature drift, or we call this as from the generalized drift velocity expression, we are going to use the generalized drift as 1 by q times F cross B by B square. But now, in order to accommodate the movement of the particle along a curved line of force, we take this force and evaluate the drift pertaining to that. So, V, we are going to call it as V curvature is equals to minus m RC phi dot square along RC cap times B phi divided by B square q, right. Now, this velocity V phi is nothing but r phi dot, which can also be called as the parallel velocity because it is along the phi direction, right. So, we can write V curvature is equals to m V parallel square by q RC times RC cap times cross B by B square. This is V curvature. This is the curvature drift velocity. Now, what you see from here is that the curvature drift velocity is dependent on the charge. So, it will be in different directions for different polarities of the charge. And more importantly, so we can write the electron curvature drift VEC as minus m V parallel square divided by QRC times RC cap cross B by B square. The ion curvature drift as mi V parallel square by QRC RC cap times B by B square. So, from this we can infer that the curvature drift velocity is proportional to 1 by RC. So, greater the radius of curvature, the drift velocity will be smaller and is proportional to 1 by B, not B square, 1 by B. So, this is something about the curvature drift. Okay. Now, what we have learned so far is we have learned that if there is a gradient in the magnetic field, we have to think of the gradient drift velocity, and if there is a curvature, there is a curvature drift velocity. But most importantly, you think of any magnetic field, it is always accompanied by gradient and curvature at the same time. So, an example is if you take a bar magnet, like this, you have the north and south pole. The magnetic flux lines will converge and diverge from its poles. Right. Now, you see, as you move radially away from the bar magnet, the magnetic field strength will decrease. That means, as you go farther and farther, its strength will decrease. So, it is safe for us to assume that there is a gradient towards the magnet. Fine. And at the same time, these magnetic field lines, they have to converge and diverge at the poles. That is the fundamental nature of the magnetic field. So, if they do not converge or diverge, that means you allow a possibility of magnetic monopoles to exist. So, if it has to converge, it has to bend towards a magnetic pole. So, this is the basic nature of the magnetic field, that it will always have a gradient and its lines of force are always curved. Maybe you take a very large distances over which the magnetic field can be assumed to be parallel, but in totality it is always curved, right. So, a realistic magnetic field always comes with these two basic properties, that it will have a gradient and it will also have a curvature. Now, we have evaluated expressions for the gradient drift as well as the curvature drift. Now, we have to find a mechanism wherein we can add these two drifts and give an expression which is valid for any magnetic field, as long as it is not varying with respect to time, right. So, we know that the curvature drift, let us say we write VR for curvature, VR we used Vc for curvature, Vc electron, Vc ion. We write a general expression without involving the charge Q to be positive or negative. We write m V perpendicular square by Q RC square B square times RC cross B. So, if you look at the earlier expression, we have made use of the unit vector which is along RC, which is RC by mod RC, right. So, this is the curvature drift. Now, one thing is very clear, VR is perpendicular to both RC as well as B, just like the V del B is perpendicular to the magnetic field itself and the gradient. So, it will find a direction which is perpendicular to both of these directions at the same time. So, as the particle is moving along the curvature, it experiences this curvature drift, and at the same time we have del B, which is minus plus V perpendicular RL by 2B square times B cross del B. So, if you recall our last class, we have used B cross dou B by dou Y. The derivative of the magnetic field is now represented as a gradient in any direction, in any possible direction, right, which can be rewritten as minus plus m V perpendicular square by 2Q times B cross del B by BQ. What did I do? RL, I have used RL is equals to m V perpendicular by QB, right, m V perpendicular square by 2Q B cube. That is why this additional Q comes and multiplies this B square, right. Now, we can write half m V perpendicular square as W perpendicular. What is W perpendicular? The kinetic energy in perpendicular direction. So, we can write V del B as minus plus W perpendicular by Q times B cross del B by BQ. So, what is the total drift the particle experiences? The total drift we can write the total drift is V del B plus VR. How can we write it? The total drift is equals to 1 by Q m V parallel square by RC square times right. So, this is the curvature drift which is taking care of the parallel component of the velocity, because the particle is moving along phi direction and this drift seems to be affecting the phi component of the velocity, which is the parallel component, and this is affecting the perpendicular component of velocity. Now, if you go back to this expression, this one you see here, So, we basically have V phi. When you have angular velocity, that is how you write the angular velocity, right. So, V phi is nothing but V parallel, which is parallel to the magnetic field. So, in your expression you have made use of this substitution only then, otherwise your expressions were basically written in V phi, right. So, this is the perpendicular and parallel components. Now, if you now we have to find a mechanism wherein we can combinedly write an expression involving both the gradient and the curvature drifts. So, this is okay. Now, for this let us take a geometry. Let us say we have x, y, z, we have the magnetic field along Bz, and there is a curvature like this, B is equals to B along phi cap, and there is a gradient which is del B. So, under that particular geometry, we write the magnetic field B as Br, B phi, Bz. So, we have Br is equals to 0, Bz is equals to 0, B phi is not equals to 0. That means the gradient the curvature magnetic field we are trying to accommodate. So, we have a situation like this in which the magnetic field lines are curved with a radius of curvature Rc, and Rc cap is the unit vector along this, where Rc cap is written as Rc by mod Rc. Right. So, if you look at this, so the coordinate system is, you have this as the phi cap direction, let us say take a point. So, this is along the curvature, let us say this is along phi cap and this is r cap. So, we can write B as B phi varying along r directed along phi. So, as you move in the r direction, in this direction, you will encounter lesser and lesser number of flux lines, but all of them are moving in the positive phi cap direction. So, this is the positive phi cap direction, right. So, thus you have accommodated the provision of gradient as well as curvature. So, this coordinate system is not actually representing the movement of the flux lines in the positive phi direction. I will try to redraw it. So, this is the direction, right. So, this it is, and you have a coordinate which is coming out of the plane, which is the z direction, the dot that I have written here. Okay. Now, if this is del B, how do you define del B? As it has a magnitude del B, let us say, and which is along r cap. So, now I hope you have understood this. Let us go back and revisit the basic geometry of the magnetic field, which is demonstrating the curvature as well as the gradient. You see here, as you go farther and farther in this direction, in the RC direction, the number of flux lines is decreasing. Let us say, okay, like this. That means there is a gradient in the magnetic field in the R direction. That is what is indicated here. But what is the direction of magnetic field? The direction is along phi cap. Now, if you are wondering what I am actually doing, we have obtained expression for the total drift. This is V total. The total drift is this. The first part is given by the curvature and the second part is given by the gradient. Now, if you look at it carefully, we have obtained these two expressions individually by considering different geometries of magnetic field. Let us say while we were doing the gradient drift, we never thought anything about the curvature. We thought it is a gradient which is present. We evaluated the average forces along all the directions. Then we use the generalized drift expression and obtain the gradient drift. We have this expression that is coming for that theory. Then while we are looking at the curvature drift, we did not thought of the gradient. We have taken a configuration in which the magnetic flux lines are moving in the positive phi direction, and if the particle is travelling along that, what is the force and what is the drift. Now, what we are doing now is we are trying to see a complete picture wherein we have taken the cylindrical coordinates, we have assumed the gradient to be spread out in the r direction. Yeah, so if this is r direction in which the gradient is present, so that means as you go to higher values of r, you are bound to find stronger magnetic fields. And the magnetic field is of course now towards the phi cap direction, right. Now, having both of these defined clearly, this is the confusion. The magnetic field itself is along phi cap, but the gradient is along r cap. Now, let us evaluate the del cross B expression. Del cross B. And so, in cylindrical coordinates, we can write it as 1 by r dou Bz by dou phi minus dou B phi by dou z along r cap plus dou Br by dou z minus dou Bz by dou r along phi cap plus 1 by r dou by dou r of r B phi minus dou Br by dou phi along z cap. How did I get this? This is the expression for curl or del cross B in the cylindrical coordinates. This is a general expression. What we are going to do is we are going to substitute this configuration of the magnetic field into this, and then we will try to see how we can get a combined expression of drift in a realistic magnetic field. So, this is how we write del cross B in the cylindrical coordinate system. We will try to make substitution of this geometry of magnetic field into this expression and try to see how we can write a single expression which involves gradient as well as curvature drifts.